Hello, today we're going to discuss about divisibility and modular arithmetic, section 4.1. Introduction. Divisibility of an integer by a positive integer produces a quotient and a remainder. Working with these remainders leads to modular arithmetic, which plays an important role in mathematics and which is used throughout computer science. When an integer is divided by a second non-zero integer, the quotient may or may not be an integer. For example, 12 divided by 3 is equal to 4. This is an integer result, whereas 13 divided by 4 is equal to 3.25. Definition 1. If a and b are integers with a not equal to 0, we say that a divides b if there is an integer c such that b is equal to a times c. Or equivalently, if b divided by a is an integer. When a divides b, we say that a is a factor or a divisor of b, and that b is a multiple of a. The notation a bar b denotes that a divides b. We also say a does not divide b. With these slanted, or something like look like an X um, notation. This symbol means A does not divide B. Example 1. Determine whether 3 divides 7 and whether 3 divides 12. Solution. We see that 3 does not divide 7 because 7 divided by 3 is not an integer. On the other hand, 3 uh, 3 divides 12 because 12 divided by 3 is equal to 4. Example 2. Let n and d be a positive integers. How many positive integers not exceeding n are divisible by d? Solution. The positive integers divisible by d are all the integers of the form dk, where k is a positive integer. Hence, the number of positive integers divisible by d that do not exceed n equals the number of integers k, with k bounded between 0 and n over d. Therefore, there are n over d positive integers not exceeding n that are divisible by d. N over d here is written in terms of greatest number function. That means any number that we generate by dividing n over d, we will round it down into the nearest integer. Theorem 1. If a, b, and c are integers where a not equal to 0, then if a divides b and a is equal to c, then a divides b plus c. If a divides b, then a divides b times c, where c here is any integer. If a divides b and b divides c, then a will divide c. Corollary. If a, b, and c are integers where a not equal to 0, such that a divides b and a divides c, then a divides m b plus nc, where m and n are integers. The division algorithm. When an integer is divided by a positive integer, there is a quotient and a remainder, as the division algorithm shows. Theorem 2. Let a be an integer and d a positive integer, then there are unique integers, q and r, where q is between 0 and d. So then we can write a is equal to dq plus r. Definition 2. In the equality given in the division algorithm, d is called the divisor, a is called the dividend, q is called the quotient, and r is called the remainder. These notation are used to express quotient and remainder. Q is equal to a divided by d. R is equal to a mod d. Example 3. What are the quotient and the remainder when 101 is divided by 11? Solution. We can express 101 to be equal to 11 times 9 plus 2. Hence, we can say the quotient when 101 is divided by 11 is 9, because 9 is equal to 101 divided by 11, and the remainder is 2, because 2 is equal to 101 mod 11. What are the quotient and remainder when negative 11 is divided by 3? We have negative 11 is equal to 3 times negative 4 plus 1. Hence the quotient when negative 11 is divided by 3 is equal to negative 4, because negative 4 is equal to negative 11 divided by 3, and the remainder is 1, because 1 is equal to negative 11 mod 3. We can never have our remainder as negative. It has to always be positive. This is something to to observe, because we could have done it in a different way, and then we would have gotten our remainder to be negative 2, but negative 2 is not allowed. Okay, we can find modular arithmetic using a circle. For instance, 12 mod 7. We say we have 12 right now, and we are finding 12 mod 7. That means to draw 7 here, we start with 0, 0, 1, 2, 3, 4, 5, all the way to 6. This is more like my radius, okay, for this modular, problem. And now we want to find 12 mod 7. So the first thing is we start from 0 and we circle one time. That takes 7 units. And then again we circle again the remaining of the units is 5 units. So we go 1, 2, 3, 4, all the way to 5 here. So that means 12 mod 7 is equal to 5. So this is another way of finding a modular or a mod of a number. For instance, 9 mod 7 is equal to 2, using the same concept that we did here in the first problem. And then the same thing here, 12 plus 9 mod 7. This is equal to 0. And then 5 plus 2 mod 7 is equal to 0. Because when we circle, we find that 7 mod 7 is equal to 0. Modular arithmetic. Definition 3. If a and b are integers and m is positive integer, then a is congruent to b modular m. If m divides a minus b, we use the notation a, with equal sign with 3 layers. B mod m is a congruent symbol. Okay, and then in theorem 3 we said let a and b be integers and let m be a positive integer. Then a congruent b mod m if only if a mod m is equal to b mod m. Determine whether 17 is congruent to 5 modular 6 and whether 24 and 14 are congruent modular 6, because 6 divide 17 minus 5, we see that 17 is congruent 5 mod 6. However, 24 minus 14 is equal to 10 is not divisible by 6. We say that 24 is not congruent 14 mod 6. These are references we use to generate all these slides. Thank you.